Hello, my dear. Let's see you again, and let's start our lecture number 15 on avionics engineering. Today's lecture topic, derivation of air data laws and relationship. You know, the object of this lecture is to show how the mathematical laws relating altitude, air density, Mach number, calibrated airspeed, free airstream temperature, and true airspeed are derived from the basic air data measurements of static pressure, total pressure, and total or sometimes indicated air temperature. Okay? I should to tell you that it should be noted that the standard atmospheric pressure is the atmospheric pressure at sea level. You remember, under the standard temperature conditions are next 15 centigrade or 22 or 288 and 15 Kelvin, and is equal 101.325 kilonewton per square meter or kilopascal. Okay, so let's start our first topic today's lecture, altitude static pressure relationship. By making certain assumptions regarding a standard atmosphere, it is possible to express the altitude above sea level at any point in the Earth's atmosphere as a single valued function of the atmospheric pressure at the point. And these assumptions concern the chemical constitution of the atmosphere, initial atmospheric conditions at sea level, and the temperature distribution throughout the atmosphere. So, these assumptions of standard atmosphere are based on statistical data and the pressure altitude, so derived can differ from the true altitude above the sea level by several thousand feet. However, as explained in previous lecture, provided the static pressure is measured accurately and the computation errors are small, all aircraft flying at a particular pressure altitude and will be flying at the same altitude, and the fact that the pressure altitude does not coincide with the true altitude and does not matter from the air traffic control aspect. A standard atmosphere also enables flight tests, wind tunnel results, and general aircraft design and performance parameters to be related to a common reference. So, the pressure altitude static pressure relationship is derived as follows. So, referring at this figure on the left part of this slide, the change pressure, delta P, okay, of air density rho, resulting from a small change of height, as you can see here, delta R, small change of height, is derived from equating the forces acting in the vertical plane on an element volume of air, from which we can see this more simple expression on the top, minus dP proportional rho g dA. Here g, as you remember, is a gravitational force. From the Gauss law, we may write the next expression, P proportional to rho times R sub A times T. Here the T capital is the air temperature in Kelvin. R sub A is the gas constant for unit mass for dry air. Combining these two equations, we can get the next expression, minus dP over P, get us G over R sub A times T capital times dH. So temperature here can be expressed as a function of altitude only, by making the following assumptions, which are based on statistical data. First, the temperature at sea level, T naught, and the pressure at sea level, P sub S naught, are assumed to be constant. Second, the temperature decreases linearly with increasing high until a high known as the tropopause is reached, above which high the temperature remains constant. Hope you remember this, okay? And until the stratopause high is reached. The region below the tropopause high is known as a troposphere. The law relating temperature T at altitude A up to the tropopause high is expressed by this equation, T proportional T naught minus LA. L here is a temperature lapse rate. So the temperature above the tropopause high stays constant at a value T sub T with star until a high known as a stratopause is reached. The asterisk here is used to distinguish the tropopause temperature, okay, from the total temperature T sub T. The region between the tropopause and stratopause high is known as a stratosphere. Fourth, at height above the stratopause, height at temperature starts to increase linearly with height, and this region being known as the chemosphere. The temperature in the chemosphere is given by the next expression here, T proportional T sub T star plus L in times the expression in parentheses H minus H sub S. Here the L, the temperature rise rate, and H sub S is a high of stratopause. The altitude pressure law is thus made up three parts covering the troposphere, stratosphere, and chemosphere regions respectively. Okay? The gravitational acceleration G at an altitude H differs from the value at the Earth's surface. G naught X and obeys an inverse square law, as explained already. So G may be described as this expression on the left up corner here. G proportionals R squared naught divided by the R naught plus H all in square times G. R here is the radius of the Earth, right? The effect of this variation is deriving the pressure altitude is very small over the normal operating altitude. And it is convenient to assume that G is constant at the sea level value. And values for the G naught, thereby simplifying the integration for equation. The value of altitude, so derived, is known as the geopotential altitude. This small difference does not matter from the point of view defining a pressure altitude, which is a single valued function of the static pressure. So, for troposphere region, we may write the temperature will be proportional T naught minus LH. So from here we may find the P sub A sub S, it will be P sub S naught in parentheses 1 minus L over T naught times H, and the power G naught over L times R sub. So attitude H will be described as the next expression. T sub naught over L in parentheses Y minus P sub S divided by the P sub O in power L R I over G naught. Power, as you see, opposite from the previous expression, right? For stratosphere region, temperature will be equal T sub T star and P sub S according to this expression. P altitude at the next. Here we have a difference. We have the logarithm expression here. For chemosphere region, the static pressure versus altitude relationship can be derived by similar process only by using substitution. T will be proportional for the T stars plus H and H minus H sub S. In this expression, we're thinking that the G equals G naught and integrating both sides between the appropriate limits. Here we can get these two expressions for P sub S and for H. Okay? Nice. The values of the constant used in the pressure altitude law is set out in this table on the left part of this slide. In SI units with the alternative units in bracket. The symbol H sub P, yeah. So is used hence was to denote pressure altitude. The formula relating P sub S and H are set out below here, on the right here, and derived by substituting the appropriate values in the table. According to that equation we see in previous slide. So for troposphere region, we may found that region is between minus 914 up to 11,000 meters times the minus 3 to 36,000 feet. So PS we will be calculating according to this expression. Stratosphere region between 11,000 up to 20,000 meters, and calculate PS we may find according to next expression. For chemosphere region, its altitude from 20 to 32,000 meters, and P sub S for this region are calculating according to the next expression. Okay? Oh, sorry. Okay. So HP here is expressed all in meters, not in kilometers. And the conversion factor to convert feet to meters, you can see on the bottom of this part. 1 feet is equal 0.3048 meters. The chemosphere region formula have been omitted for brevity as already mentioned. Are you agree? So the static pressure altitude relationship computed from the above formula is plotted in this figure. It can be shown that the difference between the pressure or geopotential altitude H sub P derived from the previous formula, which assumed that G equal G naught, and the geometric altitude h sub g derived from the above formula, which is assumed to G equal G naught. And the geometric altitude h sub g obtained by the allowing for the variation of G with altitude and is given to a close approximation over the normal altitude. This approximation hg squared over the r. R here is the radius of the Earth. As you remember, it equals 6,356.8 kilometers for latitude of 45 degrees. We do not thinking about the mountains and the sea level. Okay. As mentioned earlier, the difference is small over normal altitude. Also, it follows a square law. Okay. So, for example, if we have the difference for the 19 meter or 62.4 at the 11,000 meter, so we can find this expression in the form. Okay. Now, next topic today's lecture, variation of ground pressure. Errors due to the variation in the ground pressure from the assumed standard value are taken out of the altimeter reading by setting a scale to a given pressure. This action affects the 0 point and so alters the altimeter reading over the whole of its range by a high corresponding to the pressure set as determined by the altitude pressure law. The pressure that is set for any given occasion varies with the type of altitude indication to be used. If the standard group level pressure, usually it's 1013.25 millibar, is set, then the altimeter will read pressure altitude or barometric altitude. And if the QFE system is used, the pressure at ground level, not necessarily at the sea level, as you can see from this diagram, right? And is set, and the altimeter reads high above the ground at this point in the atmosphere and assumed as a standard. And thus, if the QFA for the airfield is set, the altimeter will read 0 on the touchdown, assuming an accurate instrument system. If the QNH system is used, the pressure at mean sea level of it computed for the region concerned is set, and the altimeter reads high above the sea level if the atmosphere is assumed as a standard. Standard regularly measured from the sea level. The different modes of high indicating in this figure. So that we have airfield altitude, and we have the according to the sea level altitude, the QFA and QNH. Let's analyze air density versus altitude relationship. The relationship between air density ρ and altitude h is derived from the equation relating the P sub s and altitude h. And using the Gauss law, P sub s proportional to ρ times r capital sub a times t. It's used to eliminate P sub s. For example, in the troposphere, we have the P sub s will be proportional to P sub naught in parentheses 1 minus L over T naught in power G naught over RL R sub A. Temperature will be proportional to T naught minus LH, and so hence we can find the relation ρ over the ρ naught. will be proportional in the parentheses, so analogical as we see in the top, yeah? And the difference only in the power, minus 1. So here we have the real naught is the density at the standard sea level condition. So standard sea level condition, we may find that P sub SO as sea level naught over R sub A over T. And the ratio rho over rho naught is referred to as the density reduction factor, rho over rho naught. So here, so often called density reduction factor. Let's see some example, as you can see on the right side. We need to compute the air density at an altitude of 10,000 meters. It's given that rho naught y 1.225 kilos per cubic meter. And we have the expression for G naught over L sum Ri. So density at this altitude of 10,000 meters will be net. We have density rho minus expression Leb's rate 6.5, 10,000 meters, or the temperature at the sea level 15 degrees, right? And the power, we have this, and we got the result O dot for 1 to 7 kilos per cubic meter. In practice, air density ratio rho over rho naught, when required, is normally computed from the static pressure Ts sub F and the measured or indicated air temperature T sub F, measured temperature. And using the following relationship, so static pressure, temperature, static temperature here, it's T sub M over 1 plus R times O 2 M squared. And relationship rho over rho naught proportional P sub F over P sub S naught times T naught over T sub F. Okay? In this case, we can get the next expression for the rho over rho naught. We have PS over PS naught is the same, and next part will be transformed a bit different. T naught parenthesis 1 plus R plus O dot M, yes, so is divided by the TF. Okay, so very simple. Next topic today lecture, speed of sound. The derivation of the formula for the speed of sound, in our case as A capital, is set out briefly as it is fundamental to the derivation of Mach number. Calibrated airspeed, static air temperature, and true airspeed from the measurement of total pressure. Measurement and static pressure and indicated air temperature. So, consider first a string tube of air of unit cross-sectional area. We have A tube here and unit cross-sectional A, through which a pressure wave is being transmitted with velocity where traveling from right to left. Imagine now the equivalent situation where the pressure wave is stationary and the air is moving with velocity where and traveling, as I just mentioned, from left to right. Consider a section at A point here, where the pressure is P and air velocity V. Let the section B on the right side represent the adjacent point of the stream tube, where the pressure of the air increases by dP, this pressure plus dP, is passing through the pressure wave, and let the velocity change by delta V, and so the density by delta rho, 0. Equating the mass flow from A to B, we may rewrite as this expression on the board. Rho AV equals, in parentheses, rho plus d rho times A, and next parenthesis, V plus delta V. Neglecting second order term, we may rewrite this expression more compact for minus V d rho equals rho dV. Force acting on stream tube of air between sections A and B, it will be the change of moment per second or mass per second time change in velocity. So in this case, we will rewrite dP equals minus rho times V dV. Combining last two equations, we may get expression for dP over d rho. It gets us V squared, right? The transmission of pressure wave closely approximate an adiabatic process because the pressure change takes place very suddenly, and consequently, there is no time for any appreciable interchange of heat. In this case, the law of the adiabatic pressure will be described as P proportional K times rho in power gamma. Gamma here is the expression Cp over Cv, specific heat of gas at constant pressure over specific heat of gas at constant volume. For normal conditions, gamma equals 1.4. And in case if the temperature K constant, we may rewrite our expression dP over T rho as a K gamma rho in power gamma minus L, or simply must equal gamma P over rho. These last two equations let at the area when we have the speed of sound and area that can be found from this expression, square root from gamma P over rho. After substitution, P equals rho times R sub A times T, and our previous equation to this will be transformed in this more simple form, more compact form, square root from gamma R sub A times T. So the speed of sound depends only on the temperature of air. And the speed of sound at the sea level in our case at A sub O, under standard pressure temperature condition, will be equal according to this one, 1.4 gamma, temperature here, R sub A here, and temperature on the right side. So in this case, R naught will be equal to this expression, 340.294 meters per second. So the speed of sound reduces with increasing altitude as the temperature decreases until the troposphere sky is reached. After that, the speed stays constant within the stratosphere sky, bends as the temperature is constant. The variation in the troposphere region is derived from the next relationship, A proportional A naught times radical 1 minus L over T naught times H. And speed of sound, we may now, from the different attitude, we can found in this data. Next, our questions to this lecture, pressure-speed relationship. The relationship between total pressure P sub T, static pressure P sub S, true air speed V sub T, and the local speed of sound is explained from first principles in this section, as it is fundamental to the derivation of Mach number, M, and calibrated airspeed. So, in our case, V sub T. And the local speed of sound is explained from the first principles in this model, as it's fundamental for the derivation of Mach number and calibrated airspeed V sub c. As already stated earlier, knowledge of the Mach number enables the correction for the kinetic heating effect to be determined, and so that the static air temperature T sub S can be derived from the measured air temperature T sub F. So let's start with first expression, subsonic speed. The total and the static pressure measurement system is shown schematically on the left figure. Consider first the case of low airspeed below Mach number equals 0.3, where the air can be considered to be incompressible, and the density, therefore, in our case, constant. In this case, the moment equation for the air flow will be described by this first expression, dP plus rho v dV must be equal 0. In the free air stream, in case the P equals P sub S and V equals V sub T, at the probe phase, P equals P sub T and V equals 0. Integrating the momentum equation between these limits get us now an expression in the middle. Integral rho from PS to PT from dP times rho integral V dV measured from V sub T to 0. And hence we can get, after integrating, PT minus PS get us 1/2 rho Vt squared. So this equation, it's a Bernoulli's equation, right? So V sub T, we may define as a radical from 2/rho times the next radical P sub T minus P sub S for low airspeed before Mach equal 0.3. However, air is a compressible fluid, and the density is not constant, right? The change in density due to the high impact pressures resulting from the high airspeed must therefore be taken into account. Assuming adiabatic flow, the relationship between the pressure and the density may be described as this expression on the right, on the top. P proportional K times rho in power gamma, from which rho may be found as 1/K in power 1 gamma times P in power 1 gamma. Substituting for rho in the momentum equation as a dP plus rho v dV equals 0, we may transform this expression and next for dP plus 1/K in power 1 gamma times P in 1 gamma times V dV must be equal 0, right? So in the free air stream, when we have the P equals P sub S and V equals V sub T, at the probe phase, when we have the P equals P sub T and the speed of equals 0, and after rearrange this equation, and integrate it between this limit, we can get the expression at the bottom. Integral from Pf up to Pt, from the P in power gamma minus P in power minus gamma times dP, plus coefficient 1/K in expression power by 1 gamma times integral from Vt to 0 for expression Vdt. All them must be equal to 0. After substituting for the K in power 1/gamma, our equations rearranging in these expressions. From equations, you will remember k in power 1 over gamma. It's proportion of p sub s in power 1 over gamma over the rho. We may find next expression pt over ps. We have expression on the parentheses, 1 plus gamma minus 1 over 2 times rho over gamma times p sub s times v sub t squared and parentheses gamma minus gamma without 1. If we know that the gamma times ps over rho get us a squared, and putting that gamma equal 1.4, the above equations get us expression for pt over ps. 1 plus O dot 2 in a nominative vt squared, in denominative a squared, all of them in power 3.5. And so that's the q sub c proportions p sub s. In parentheses, we have as a store in this part minus 1. Okay? This was subsonic speed. In case we have supersonic speed, the aerodynamic theory involved in deriving the relationship between Pt, P sub T over P sub S, and Mach number. Mach number is V sub T over A at the supersonic speed, in case when Mach number more higher than 1. Is beyond, but this expression beyond the scope of our analysis. The formula relating pressure ratio P sub T over P sub S and Mach number derived by a relay and therefore set out below without further explanation. All be given as simplification. Why? Because it's not our studies thermodynamic and aerodynamic. Okay? So we're using this expression as we know. And this can be found in suitable aerodynamics textbooks for some persons who want to know more. So we use only expression in this case, Pt over Ps as this expression. After substituting gamma equal 1.4, we can get this expression in a more compact form on the bottom. Okay? And P sub S will be P sub S, and parentheses we can see next expression on the line. Right? Next question, Mach number. Mach number can be derived from the previous equation for the subsonic and supersonic regions, respectively, only by substitution as a Mach number equal V sub T over A. Mach number equals V sub T over A. So for subsonic speed, we found our expression P sub T over P sub S. It's 1 plus O dot Mach squared, all of them in power 3.5. For supersonic speed, P sub T over P sub S get us a bit complicated expression, 166.98 times m in power 7. In denominator, we have 7 Mach number squared minus 1, and solve this expression in power 2.5. The pressure ratio P sub T over P sub S is plotted against Mach number on the right side for the S for subsonic, S for supersonic region, before 1 Mach number 1 subsonic region, and after 1 we have supersonic region. Okay? Next question, calibrated airspeed. Calibrated airspeed V sub C can be derived directly from our previous equation for the subsonic and supersonic cases respectively. only by substituting for sea level condition. That is, P sub S will be transformed as a P sub S naught, and V sub T, transformed into V sub C according to definition. So, for subsonic speed, in case we have the V sub C less than R, no higher than A sub naught, we may find expression for QC equals P sub S naught in parentheses 1 plus O dot 2 V sub C over A naught in square, and all expression in power 3.5. After that, minus 1, and get all this expression for P. A simplexer approximate expression relating for the QC and V sub C can be obtained by applying by the binomial expression for the inner factor. Binomial expression, and here you can see this part. And noting that A naught square is proportional gamma P sub S naught over rho naught. After that, we may find our expression for QC. In this case, it's approximately equal 1 over 2 rho naught VC square, and this expression, they do not change before. Okay? So, the error in this expression being about 1.25% in case when VC equals A naught. Its expression 661.5 kilonewtons. But it should be noted that the exact formula for our equation is used to compute calibrating airspeed. The approximate formula is useful, however, for appreciating the effect of increasing airspeed and Mach number, and low airspeed, and at low airspeed. It can be seen that P sub C equals 1 over 2 on the bottom times rho naught times VC square. In case of supersonic speed, when we have the VC higher than A naught, referring our equation will be presented in this case. QC proportional PC, and we see in parentheses this expression. The impact pressure, Q sub C, is plotted against the calibrated airspeed, as you can see on the left part side. Before the Mach number 1, we have expression for subsonic. After that, supersonic speed. We should notice the very low impact pressure of 16.3 millibars at a calibrated airspeed of 51.5 meters per second. It's nearly 100 kilonewtons. And the very high impact pressure of 1,456 millibars at a calibrated airspeed of 412 meters per second, or 800 kilonewtons, approximately get us Mach number 1.2 at sea level. Next question, static air temperature. As already mentioned, the temperature sensed by a thermometer probe in the airstream is the free airstream temperature plus the kinetic rise in temperature due to the free airstream, due to the air being brought partially or wholly to rest relative to the sensing probe. The kinetic rise in temperature can be obtained by application of Bernoulli equation to compressible flow and assuming the pressure changes are adiabatic without change of heat. For unit mass of air, we can write our expression, Bernoulli expression, in this case, P1 over rho 1 plus half V1 squared plus energy 1 equals P 2 over rho 2 plus 1 over 2 V2 squared plus NSB. Left part side and right part side represents the pressure, density, velocity, temperature, and internal energy at both 2 points 1 and points 2 in a streamline flow, namely in the free airstream and at the probe. Okay? So P1 over rho 1 proportional R8T1 and we may write the same PO2 over rho 2 proportional R sub A times T2. In the free air stream, when we have V1 as a VT and T1 SPS, at the stagnation point of the probe, in case V2 equals 0 and T2 equals T sub T, and substituting this value, equation gives us next expression here. 1 over 2 VT squared E2 minus T1 plus RA times TT minus T sub S. The change in internal energy becomes heat and gives by this expression E2 minus E1 proportional JCV in parentheses T sub T minus T sub S. Here J is the mechanical equivalent of heat, or simply telling as a called it Joule's constant. And CV here is a specific heat of air at constant volume. And hence our equation will be transformed in the next expression here. From the thermodynamic theory, we know that R sub A equals J times Cp minus Cv. Cv we already know, it's a specific heat of air at constant volume. And Cp, we already maybe now or maybe some specific heat of air at constant pressure, right? So combining last two equations, we can find expression on the right at the bottom. 1 over 2 Bt squared proportions RACP over Cp minus Cv and times T sub T minus T sub S. Rearranging and substituting in case gamma equals Cp over Cv, we may rewrite our expression in this compact form. T sub T minus T sub S proportionals gamma minus 1 over 2 times 1 over gamma times R sub A times Vt squared. We know that the A squared proportionals gamma times R sub A times T sub S. Substituting this expression for gamma R sub A and putting gamma equal 1.4, we may find expression for Ts at this very simple expression. Constant R, known as the recovery factor, and generally introduced into the above equation with conditions that value being dependent on the temperature probe installation. And Ts we may rewrite in form as you can see on this expression. Tm here is the measured or indicated air temperature. In case you have a stagnation point, in case R equals 1 and T sub M equals T sub T, and R is normally assumed to be constant, and it can vary slightly due to change of heat transfer from the probe with altitude. Significant variation can also occur flying through rain or cloud. Okay. Next question, true test. The computation of the temperature of free streams T sub S enables the local speed of sound A to be established as this expression on the top. Square root from gamma times R sub A times T sub S. True airspeed V sub T can be then obtained from the Mach number m times A, or m Mach number times square root from gamma RA times T. And hence, V sub T may be rearranged in this expression here on the middle of this line. And V sub T get us next expression. This can be readily converted to kilonewton using the conversion factor 1 meter per second given 1.9425 kilo. The air data formula are set out in this table. Pressure error. The pressure measured at the pi-top head and the static orifice are not exactly equal to the true variation. The error in the total pressure measured at the pi-top probe and is usually very small provided the incidence angle of the probe to the airspeed vector and is very, very small. So the error in the static pressure measurement, however, can be significant and is due to disturbance of the airflow near the detecting orifice by the pressure head itself and by the aircraft structure. So, to minimize the latter effect, the pitostatic probe is often mounted in front of the foremost part of the aircraft, in which case disturbance due to the aircraft disappears above the speed of sound. The normal error pattern for this type of installation is for the error to build up to a maximum at m equal 1, and for it then suddenly to drop to a low value of supersonic speed. Pressure error for the aircraft installation is determined by extensive flight testing and in general is a function of Mach number and altitude. This function is often referred to as the static source error correction, SSEC, and can be a relatively complex nonlinear function around Mach number equal 1. So the static source error correction is generated by the air data computer, and correction corrects applied to the approximate output. So let's come to the next question, air data sensor and computer. The key air data sensors, as already mentioned, comprise two pressure sensors and the temperature sensor. The temperature sensor generally comprises a simple resistance bridge with one arm of the bridge, consisting of a resistive element exposed to the airstream, and the resistance of this element being a function of temperature. In terms of technology, the temperature sensor is a relatively simple and straightforward device, which fairly readily meets the system accuracy requirement. The pressure sensor, however, merit considerable discussion because of their very high accuracy requirement, and thus influence on the overall system accuracy, long-term stability, reliability, and certainly overall cost. A very wide variety of air data pressure sensors has been developed by different companies and organization or technical establishment, or 5. You name an effect which is a function of pressure and some organization has developed. Or you may say, or tried to develop, a pressure sensor exploiting it. Air data pressure sensor require an extremely high accuracy, which will be explained shortly, and involve a long, expensive development to establish and qualify a producible or competitive device. Like most sensors, they not only sense the quality being measured, but they can also be affected by temperature changes, vibration, shock, acceleration, humidity, etc. So, the art of sensor design is to minimize and, if possible, eliminate these effects on the sensor. Let's study accuracy requirements. Initially, let's start with a static pressure sensor. Typical air data static pressure sensors have a full-scale pressure range from 0 to 130 kilopascal and a minimum non-derangement pressure of the 390 kilopascal or 3.9 atmosphere to cover mishandling in testing. They are required to operate over a temperature range from -60 centigrade up to 90 centigrade, or even higher. Why beneath higher? We have the hypersonic speed flight. So the effect of a small error in static pressure measurement and the resulting altitude error can be derived by rearranging our equation and get this expression. Minus dP over P proportional G over R sub A times T times dH. In the troposphere, we may find, from this expression, we can find our dH expression, right? For the troposphere, this expression will be a bit more complicated forming this map. In the stratosphere, it's transformed in the next one. The effect of 100 Pascal error is in static pressure measurement at sea level is equal to this expression on the right side on the top. We calculating these values at the temperature 15 degrees, yes, and these P are A sub T, and given 1 over P, and get us 832 meters. So, however, the effect of 100 Pascal error in static pressure measurement at an altitude of 13,000 meters, when the static pressure is 16.5 kilopascal for 165 megabar is equal to this expression. So the need for accuracy in the static pressure measurement at the high altitude used in cruise flight and can be seen bearing as mine ATC high level separation of 1,000 foot. A major part of the error budget in the static pressure measurement is the inherent pressure error due to the installation and location of the static pressure orifice. And this means that the pressure sensor may not be measuring the true static pressure. This pressure error, or position error, as it is sometimes called, has to be determined experimentally and is a function of Mach number and inside. the uncertainty in this pressure error can be of the order of 100 to 150 pascal, so that the error contribution from the pressure sensor should be as small as possible, say less than 30 pascal. And this would give a worst case or overall error. It's equal 150 plus 30 that get us 180 pascal at 13,000 meters altitude in the measurement of the static pressure, which corresponds to an error in the pressure altitude of 69 meters, of which the static pressure sensor contribution get us the value less than 12 meters. The errors in static pressure measurement over the low altitude pressure range should also be less than 30 pascal. And this ensures the altimeter will read the true altitude on landing with 3.3 meters. No, approximately 11 feet, providing the current ground pressure has been set in and is known to an accuracy of 0.1 millibar. Modern technology air data pressure sensor generally meet or better these figures and achieve accuracies which approach those of the pressure standard used in calibration. But it should be noted that an accuracy of 10 pascal in 100 kilopascal corresponds to an accuracy of 0.01%. The pressure sensor must also have a very high resolution in order to be able to generate a rate of change of altitude H out with the required dynamic range. A typical figure aimed at for high resolution is better than 0.03 meter or 0.1 feet at sea level, which corresponds to a pressure resolution in the region of 0.1 pascal. Next step, total pressure sensor. Total pressure sensor. A typical total pressure sensor has a full-scale pressure range from 0 to 260 kilopascal. The figure of 260 kilopascal corresponds to a calibrated airspeed of 426 meters per second. Minimum non-derangement pressure is of the order of the 3 times full-scale pressure to cover mishandling in testing. You know, airspeed of 426 meters per second get us 828 kilometers, because civil aviation used namely imperial figure. The accuracy requirement for the total pressure sensor are every bit as exact as those required from the static pressure sensor. So using a total pressure sensor and a static pressure sensor to measure impact pressure, exactly P sub T minus P sub S, yes, to measure impact pressure, here this expression, requires very high accuracy from both sensors, as it involves taking the difference of two large comparable members at low airspeed, as the impact pressure is small. The effect of error is measuring the impact pressure at low airspeed can be derived from this expression. QC equals 1/2 times rho times V sub T squared. And hence we may found as a QC, we may found as a DQC, it's a rho VT times dV sub-T. Sorry, one moment. So next, our topic, pressure sensor technology. Two basic types of pressure sensors have now become well established in all modern digital air data systems. Also, there are other types of the pressure sensor in service. Attention has been concentrated on these two types as they account for most of the modern systems. The two main types can be divided into vibrating pressure sensor and solid-state capsule pressure sensor. Let's start with vibrating pressure sensor. The basic concept of this family of sensors is to sense the input pressure by the change it produces in the Marshall resonant frequency of a vibrating mechanical system. The output of the sensor is thus a frequency which is directly related to the pressure being applied. And this frequency can be easily measured digitally with very high resolution and accuracy without the need for precision analog to digital conversion security. And this confers a significant advantage as it enables a very simple and very accurate interface to be achieved with a microprocessor for the subsequent air data computation. The vibrating cylinder sensor is shown schematically in this slide. The pressure sensing element consists of a thin ball cylinder with the input pressure acting on the inside of the cylinder and with the outside at zero vacuum reference pressure. The cylinder is maintained in a hoop mode of vibration by making it part of a feedback oscillator by sensing the cylinder ball displacement, processing and amplifying the signal and feeding it back to a suitable force producing device. Electromagnetic drive and peak of coils are used so that there is no contact with the vibrating cylinder. The vibrating cylinder sensor is also density sensitive, as the air adjacent to the cylinder wall effectively forms part of the mass of the cylinder, so that a change in air density produces a small change in output frequency. And this change, however, is much smaller than that due to pressure changes. So, the air density and pressure are directly related so that this effect can be allowed for when the sensor is calibrated. The small changes in density due to temperature variations together with the very small changes in the modulus of elasticity of the cylinder material with temperature can be compensated by measuring the sensor temperature and applying the appropriate corrections. And this type of sensor is extremely rare. The very high Q of the cylinder conferring for very low susceptibility to vibration and shock, and the absence of moving parts, which enables it to withstand very high acceleration environment. The inherent simplicity and very low power consumption enables a very high reliability to be achieved together with very high accuracy and long-term stability. Acknowledgement is made to Schlumberger Industries for permission to publish the illustration of this figure of their type 3088 pressure sensor. Schlumberger Industries have developed the vibrating cylinder type of pressure sensor to an outstanding performance and reliability level. Their pressure sensors have achieved very wide-scale usage in air data systems manufactured by several major avionics companies for large number of military and civil aircraft worldwide. Next up, a solid-state capsule pressure sensor. This type of pressure sensor consists essentially of a capsule with a relatively thin diaphragm, which deflects under the input pressure. They are fabricated from materials such as silicon, quartz, fused silica, or special ceramics. Figures on this slide illustrate the basic construction. These materials exhibit virtually perfect mechanical properties, with negligible hysteresis and very stable and highly linear stress or strain characteristics. The modulus of elasticity variation with temperature is very stable and can be readily compensated by measuring the sensor temperature. The deflection of the diaphragm is linear with the input pressure. That's very nice. But it's also very small, and a number of techniques are used to measure this deflection. This will be discussed a bit later. Semiconductor technology is used in the fabrication of these sensors and is together with the absence of moving parts, which has led to the description as a solid state. The technology also enables very small sensors to be fabricated with excellent repeatability because of the semiconductor processes used. The deflection of the solid-state capsule under pressure is typically only 25 up to 50 micrometer for full scale, or even less. The technique which have been adopted to measure this very small deflection we will be described a bit later. Okay. So next, our part is the integral strain gauge. Now, piezoresistive network or bridges are ion implanted at the edge of a thin silicon diaphragm. Application of pressure causes the diaphragm to deflect, thereby deforming the crystal lattice structure of the silicon, which in turn causes the resistance of the piezoresistive element to change. The piezoresistive elements are connected in a Wheatstone's bridge configuration as shown in this figure, with two opposite resistive elements of the bridge located radially and the other two located tangentially of the diaphragm. The applied input pressure causes the resistance of the radial element to decrease and the tangential element to increase, or vice versa, depending on whether the pressure is increasing or decreasing, and so unbalances our Wheatstone bridge. Very popular element in sensor technique. The output of the bridge is proportional to the both pressure and temperature, as the modulus of elasticity of silicon is temperature dependent. A temperature-sensitive resistive element is therefore incorporated into the diaphragm to measure the temperature, and so that the temperature-dependent error, which can be corrected in the subsequent processing of the sensor output. These temperature-dependent errors are very stable and repeatable. A precision analog to digital A to D conversion circuit is required to convert the sensor analog voltage output to a digital output. The supporting electronics, including the individual device characterization, A to D conversion, and digital interface to the outside world, can all be incorporated in the sensor. This modern microelectronic technology. And this technology is sometimes referred as the small sensor technology. Capacitive peak-off. An alternative technique is to deposit a metallic field on an area at the center of the diaphragm to form a capacitive element, or peak-off, whose capacitance changes as the diaphragm deflects under the pressure. And this forms part of a capacitance bridge network. And this figure shows the device construction and how this works. A correctly designed capacitive peak-off bridge combination can have extremely high resolution and can detect the incredibly small changes in capacitance resulting from minutes deflection of the diaphragm. It is noteworthy that the highest solution yet achieved in an angular or linear displacement sensor has been achieved with a capacitive peak-off, leaving the optical measuring techniques orders of magnitude behind. This type of pressure capsule is fabricated from brass, fused silica, or special ceramic material. The variation of the modulus of elasticity with temperature in these materials is less than with silicon. An integral temperature sensor is incorporated in the cup to enable the temperature-dependent error to be compensated. The capacitive peak-off and bridge configuration must be designed and so that it is not affected by changes in the stray capacitance inherent in the lead-out wire and screen. As these changes can become variable or even exceed the very small changes due to the input pressure. A precision A to D conversion is required to provide the required digital output. But it should be noted that the solid-state capsule types of pressure sensor have an inherent sensitivity to acceleration because of the mass of the diaphragm. The sensitivity is small and can generally be ignored if the pressure sensors are mounted so that their sensitive axes are orthogonal to the normal acceleration vector. The types of pressure sensors described in all parts and used in modern digital air data systems. In a highly competitive market, all meet the requirement. As the saying goes, you pay your money and you take your pick. Today, very popular. And for us, let's start another topic of today's lecture, air data computing. A flow diagram of the air data computational process is shown in this slide. We have two components, static pressure and total pressure. We have the correct block, and after that we make computing and calibrate the result. So the static pressure can be computed at suitable increments of altitude from minus 914 up to 11,000 meters. And the data stored in a table lookup stored using the appropriate formula related static pressure and altitude. So in this case, P sub S will be expressed in this linear form. For the stratosphere, from 11,000 up to 20,000 meters, P sub S should be calculated according to this expression. And for chemosphere, as altitude from 20 up to 32 kilometers altitude, get us expression for PS as this one. So the appropriate pressure altitude corresponding to the measured static pressure can then be derived from the table lookup stored in conjunction with a suitable interpolation algorithm. Let's start with the vertical speed hp dot. The vertical speed or rate of change of altitude hp dot is derived from the rate of change of static pressure ps dot using the basic formula related to differential expression dh proportional to. And in this case, our expression for hp dot will be according to this expression. And this can be computed from the actual measured and corrected air temperature value, or from the standard atmosphere pressure. The latter is the usual case, so that HP, H sub P, is a purely a function of P sub. For the troposphere, H sub P dot will be calculated according to this expression. For stratosphere, it will be more simple expression. Deriving H sub P dot by differentiating P sub S to generate P sub S dot, and then multiplying essentially 1 over P sub S enables a better resolution to be obtained with fewer computational delay. Mach number, the pressure ratio PT over P sub S can be computed at suitable increments of Mach number, and the results stored in the table lookup store using an appropriate formula. For subsonic speeds, P sub T over P sub S will be very simple expression, 1 plus O dot 2 m squared, and all of them in power 3.5. For supersonic speed, this expression will be a bit more complicated, but not very. The actual pressure ratio P sub T of P sub S is then computed from the measured total pressure P sub T and static pressure P sub S. The appropriate Mach number corresponding to this computed pressure ratio is then derived from the table lookup stored in conjunction with a suitable interpolation algorithm. Calibrating airspeed, the impact pressure, it's a Q sub C, can be computed at suitable increments over the range of calibrated airspeed. Say 25 meters per second or 50 kiloknots up to 400 meters per second or 400 kiloknots, and the results stored in a table lookup store using the appropriate formula. So if we have subsonic, V sub C, expression for QC will be next. If we have supersonic, V sub C higher or more than 340 speed of sound, so QC will be in this form. C is derived by subtracting the measured total and static pressure. The appropriate calibrated airspeed corresponding to this impact pressure is then derived from the table lookup store in conjunction with a suitable interpolation algorithm. Static air pressure, air temperature, sorry. The static air temperature T sub F is derived by computing the correction factor 1 over 1 plus R times O dot 2 m squared, and multiplying the measured or indicated air temperature, T sub m, by this correction factor. So we can this expression. True airspeed V sub T is derived from the computed Mach number and the computed static air temperature, T sub air, and so represented very simple expression here in the book. So the air data computation can be carried out by any modern microprocessor or microprocessor with more than 16 bits. So the software to carry out this task being relatively straightforward. It's usually so popular on the drone. Computations are typically carried out at an iteration rate of 20 GHz. Also, fly-by-wire flight control system may require a faster integration rate, up to 80 GHz. A more exacting software task is the generation of the software to perform all the built-in tests, big IT, and enable fault diagnosis to module level to be achieved. Next topic today's lecture, angle of incidence sensor. The importance of angle of incidence information has already been briefly explained. I hope you remember. Knowledge of the angle of incidence can become particularly important at the extremes of the flight envelope, when high values of incidence are reached and the limiting conditions approach. Many aircraft have incidence sensors installed so that the pilot can ensure the aircraft does not exceed the maximum permissible angle of incidence. Incidence sensors are also essential sensors for a fly-by-wire flight control system, as mentioned earlier, and a redundant failure survival system of sensors is required. It may also be necessary to measure the slide slip incidence angle, usually called as a beta, slide slip incidence angle. A typical incidence sensor comprises a small pivoted vane suitably located on the aircraft fuselage, near the nose of the aircraft. The vane is supported in the low friction bearing so that it can align itself with the incident airflow under the action of the aerodynamic forces acting like a Witt's wave. The angle of vane relative to the fuselage datum, and hence the angle of incidence, is measured by a suitable angular position PO, such as a synchro resolver, the output of which can be readily digitized. But it should be noted that an incidence sensor measures indicated angle of incidence, which must be converted to a true angle of incidence by an appropriate correction formula, which is a function of Mach number. It is also possible to locate the pitot probe on the way, together with the static pressure orifices, to form an integrated unit, which together with the appropriate sensor measures angle of incidence, total pressure, and static pressure too. And this type of integrated pitot probe or incidence vane is being adopted on several new high-performance aircraft, as it minimizes incidence contamination effect on the pressure measurement at high angles of incidence, as well as providing a compact integrated solution. The integrated air data transducer ADT is illustrated in this figure. This figure from lecture number 5 from beginning. And this figure is an exploded view showing the ADT assembly, integrated air data transducer. It's on the schematic to see how this is work. I hope you enjoyed this lecture, and I'm looking forward to seeing you next time to continue this lecture talk. Okay? Bye.